Somewhere in a sealed laboratory, a single gray metal pellet sits inside a vial of oil. It looks harmless, almost forgettable, but the moment it touches water, everything changes in less than 1 second. A flash of violet fire, a shockwave, and sometimes, a blast powerful enough to shatter thick glass and send shrapnel flying across a room. This is not fiction. This is cesium, and what happens when it meets water is one of the most violent reactions in all of chemistry. But here's the real question nobody talks about. Why does something so simple as touching water cause an explosion this extreme? The answer goes deeper than most people realize, and by the end of this, you will never look at a glass of water the same way again. Cesium sits quietly on the periodic table, tucked into a family of elements known as the alkali metals. On the surface, this group seems unremarkable. Soft metals, silvery color, nothing that screams danger. But alkali metals share one defining trait. They are desperate to lose a single electron. And the lower you go on that column, the more desperate they become. Lithium reacts gently with water. Sodium fizzes and can catch fire. Potassium explodes with a satisfying pop. But cesium sits near the very bottom of that list, and that position changes everything. At first glance, this metal barely resembles something dangerous. It has a soft, golden shine, almost buttery in appearance. It melts at just under 28 degrees Celsius, meaning it could turn liquid from the warmth of your hand alone. But that softness is deceiving, because underneath that gentle golden surface is an atomic structure so eager to react that even the smallest drop of moisture can trigger catastrophic failure. Here is where things start to escalate. When cesium touches water, it does not simply dissolve or fizz like other metals. It reacts almost instantly, tearing electrons away from water molecules with terrifying speed. This reaction produces cesium hydroxide, one of the strongest bases known to chemistry, and it releases hydrogen gas in the process. That alone would be interesting, but not explosive. The real danger comes from what happens next. The reaction generates so much heat, so quickly, that the surrounding hydrogen gas ignites almost instantly, and because cesium reacts faster than sodium or potassium ever could, that ignition happens in a fraction of a second, before the gas has time to safely disperse. The result is not a slow burn. It is a violent, concentrated explosion. But what most people don't realize is that size does not matter here. You might assume a large chunk of cesium is required to cause serious damage. It is not. Even a piece smaller than a fingernail can create a blast strong enough to crack glass containers or send water flying several meters into the air. In viral lab demonstrations, scientists have dropped tiny cesium samples into bathtubs, only to watch the explosion blow the tub apart entirely. This is not a controlled fizzle. This is raw chemical energy, unleashed instantly. However, this is where things take a serious turn. Because of how unstable and dangerous cesium becomes around water, it cannot simply be stored in air like most metals. Even the moisture naturally present in the atmosphere can trigger a reaction. To prevent this, cesium must be sealed inside airtight glass ampoules, often submerged in mineral oil or kept under a vacuum, completely isolated from any trace of humidity. Handling it requires extreme precision, protective shielding, and controlled environments, because a single mistake, a single crack in the container, could set off an unplanned and dangerous reaction. This is also why cesium is almost never seen in its pure metallic form outside of laboratories. What most people encounter, if they encounter cesium at all, is not the metal itself, but cesium compounds, which are far more stable and behave nothing like the explosive element locked away in research facilities. But if cesium is this unstable, this violent, this difficult to contain, why does it matter at all? Why would scientists continue working with something so dangerous? Here is where the story shifts from destruction to something far more surprising. Despite its explosive nature, cesium holds a role that quietly shapes modern civilization. One particular isotope, cesium-133, became the foundation for something almost impossible to imagine: the definition of time itself. Inside atomic clocks, cesium atoms vibrate at an incredibly precise and unchanging frequency, over 9 billion times per second. This frequency became so reliable that in 1967, the world redefined the length of a second based entirely on cesium's atomic behavior. Every GPS satellite orbiting the planet right now depends on cesium-based atomic clocks to keep global positioning systems accurate down to mere meters. Every time your phone tells you exactly where you are, cesium is working silently behind the scenes to make that possible. That means the same element capable of shattering glass in an explosive reaction is also the reason your navigation app knows exactly where you are standing. A single element, capable of both total destruction and unmatched global precision. That contradiction alone makes cesium one of the most fascinating substances ever discovered. But the story does not end there. Cesium also plays a critical role in industries most people never think about. It is used in drilling fluids for oil and gas extraction, where its dense properties help stabilize extreme underground pressure. It appears in specialized glass manufacturing, infrared technology, and even in certain medical imaging applications. In each of these cases, cesium is handled in carefully controlled forms. far removed from the explosive reactivity of its raw metallic state. Yet despite all these advanced uses, one radioactive isotope of cesium carries a darker reputation. Cesium-137. Unlike stable cesium-133, this isotope is a byproduct of nuclear fission. Produced inside nuclear reactors and during nuclear weapons testing, it became infamous following major nuclear disasters, including Chernobyl and Fukushima, where radioactive cesium contamination spread across surrounding land and water systems for years afterward. This isotope does not explode like pure cesium metal, but its radioactive decay poses long-term health and environmental risks, making containment and cleanup an extraordinarily difficult and expensive challenge. So now the picture becomes clear. Cesium is not simply a party trick for viral chemistry videos. It exists on a spectrum. On one end, an explosive reactive metal capable of shattering containers with a single touch of water. On the other, an isotope so precise it defines global timekeeping and satellite navigation. And somewhere in between, a radioactive form capable of contaminating environments for generations. This is what makes cesium unlike almost any other element on the periodic table. Most elements have a single defining characteristic. Cesium has several, and they exist in direct contradiction to one another. Destruction and precision, danger and utility, instability and reliability. And this leads to the final unsettling thought. The next time you check your phone for directions, remember that deep inside an atomic clock, cesium atoms are vibrating with mathematical perfection, keeping your world synchronized down to the nanosecond. And somewhere else, locked away behind reinforced glass in a laboratory, another piece of that very same element sits in complete isolation from moisture, because a single drop of water is all it would take to turn calm into chaos. Two extremes, one element. And a reaction so violent, scientists still handle it with extreme caution, even after more than a century of study. So the real question is not why cesium explodes in water. The real question is how something this dangerous became something the entire world quietly depends on every single day.